I've been in networking for over a decade and decided to make some content to try to help others understand this industry. Let's talk about the Address Resolution Protocol, or ARP. The goal is to understand why we need it and how it works. So, when a device is sending a message to another device, it has to be able to construct the layer 2 and layer 3 headers. Part of those headers are the destination addresses. So, at layer 3, we need to know the destination IP address, and at layer 2, we need to know the destination MAC address. Now, the IP address is a logical assignment, and that can change over time. An endpoint can move from one network to another network and get a different IP address. The MAC address, however, that's something that is typically burned into the device interface. And so that typically doesn't change. So when a device is moving from one network to another network, that new network needs some way of learning what that MAC address is for the endpoint. So the way that we do this mapping is with the ARP table. The ARP table maps the IP address of a device to the MAC address. So when a message is being sent to an IP address, the sending device can check its ARP table to determine which MAC address should be used as the layer 2 destination. Each device that operates at layer 3 has its own ARP table, and it needs to reference that when it's creating that layer 2 header. So we know what the layer 3 destination is. We got to figure out what that layer 2 destination is. The ARP table is what holds that information. The ARP table could have static entries in it. You can specifically hard code that I want this MAC address always to be referencing this IP address, or it can be used dynamically. And that is typically how it's done. Is the ARP table is populated dynamically based off of traffic. So we'll take a look and see how this works. So here we have PCA, and it wants to send a message to another device. It happens to be PCB, but what PCA knows is that it has a destination address of 1.1.1.2. So we've looked before at how the information passes down from layer 7, 6, 5, 4. Layer 4 segment gets passed to layer 3 to the network layer. At this point, PCA has to add a layer 3 header that has the source and destination IP addresses. So PCA has an IP address of 1.1.1.1, and it knows that it has to put that as the source address. So it puts that in the header as the source IP. It also knows that it wants to send this message to IP address 1.1.1.2. So it can put that into the destination IP address. Now that has a layer 3 header, this is called a packet. It gets handed down to layer 2. At layer 2, another header has to be added, which contains the source and destination MAC addresses. So PCA knows its own MAC address is all A's, and so it can put that as the source MAC address. But now PCA needs to put the MAC address for the device that has the IP address of 1.1.1.2. So in order to figure that out, PCA looks in its ARP table to see if there's an entry for an IP address of 1.1.1.2 and that has a corresponding MAC address. In this example, we're going to say that PCA doesn't have that entry. So now PCA, it can't complete the layer 2 header for the message that it wants to send. So since the destination IP address is part of the same network as PCA, PCA knows that the destination is part of its layer 2 broadcast domain. This means that PCA is actually able to reach that destination at layer 2. This point is critical here because if the destination is part of PCA's layer 2 broadcast domain, then it can send a layer 2 broadcast and be able to reach that destination. So if PCA could receive a packet that had a source IP of 1.1.1.2, then PCA would also be able to determine what the MAC address of that device is because it would be called out as the layer 2 source of that packet. So PCA needs to try to get whatever device has the IP address of 1.1.1.2 to send it a message so that PCA can look at what the source addresses are to figure out how to send traffic back to it. So PCA is going to put this current message that it wants to send on hold for a moment, and it's going to craft a special message called an ARP request. This is intended to make the device that has the IP address of 1.1.1.2 send a message to PCA so that PCA can populate its ARP table and figure out the corresponding IP to MAC address mapping. So now PCA, it just wants to know what the MAC address is for the destination IP address of 1.1.1.2. So PCA only needs to get the ARP request to the layer 3 destination. There's no layer 4 through 7 on this. We're just talking layers 1 through 3. So this means that we don't really have to have a bunch of other information in this ARP request. We only have to go to layer 3. We don't have to go through layer 4 up to 7. So this can be a very small packet here with this ARP request. So PCA is going to put a source address of itself, which is 1.1.1.1, and it knows it's trying to get to the destination IP of 1.1.1.2, so it puts that in the layer 3 header just like we saw before. Now PCA sends this down to layer 2 for another header to be added. At this point, PCA puts its own MAC address as the source, which is all A's, and it doesn't know the MAC address of the destination, so we're at the same point we were before. But remember, we can reach this endpoint with a broadcast. So since we're part of the same broadcast domain, PCA can use a destination MAC address of all F's, and that's going to broadcast this message to everything within its layer 2 broadcast domain. So PCA sends this frame out with a destination MAC address of all F's, and it's going to be received by all devices that are in the broadcast domain. So every device, they receive this frame, they look and see that it has a destination MAC address of all F's. So by definition, they all have to assume that they are the destination at layer 2, and so they remove that layer 2 header, and then now they can see the layer 3 header. But all the devices just saw that they received a packet that had a source MAC address of A and a source IP address now it sees as 1.1.1.1. So what they can do is update their ARP tables and look and see, do they have an entry that maps IP address 1.1.1.1 to MAC address A? If they don't have that entry, then they put that in their table. They have all updated their ARP tables because they've received a packet from their local network there, and then they know that they can update those addresses. So now they look at the destination IP address, and all the devices except one end up looking at that layer 3 destination of 1.1.1.2 and determining that this is not intended for itself. So every device on the network, they're going to drop this at this point because they are not the layer 3 destination, except for PCB. Because PCB does have the IP address of 1.1.1.2, so it knows that it is the layer 3 destination. So now it's reached the layer 3 destination. PCB knows that there's a device out there that has an IP address of 1.1.1.1, and it has sent an ARP request to it, to PCB. And so PCB needs to do something. It's going to send an ARP reply back to the sender. So PCB creates a layer 3 header for the ARP reply, and this has a source address of 1.1.1.2 and a destination address of 1.1.1.1. So source address is PCB. The destination is going to be the IP address of PCA because that's the IP address that it received the ARP request from. Then PCB hands this packet to layer 2 so that a layer 2 header can be added. PCB puts its own MAC address as the source, which is all B's for this example. Then it consults its ARP table to see if there is an entry for an IP address of 1.1.1.1. Well, PCB does in fact have that ARP entry because It just got that broadcast, that layer 2 broadcast from PCA. And when it did that, it updated its ARP table. So PCB has a mapping in its ARP table that says IP address 1.1.1.1 is mapped to MAC address of all A's. So now PCB can put that into the layer 2 destination, and it has the information it needs for this ARP reply to send that back to PCA. When PCA receives the ARP reply, again, it checks the layer 2 destination and sees that the MAC address of all A's is its own MAC address. So it has reached its layer 2 destination. So PCA can remove the layer 2 header and then look at the layer 3 header. PCA sees that the source IP address is 1.1.1.2, and now it can also check its ARP table to see if there's an entry for that IP. PCA looks in its ARP table, sees that there isn't an entry there for the 1.1.1.2 IP address, and so it adds that in there. And it maps IP address of 1.1.1.2 to MAC address of B. Now PCA has everything it needs to complete its information for the message that was on hold there. And now this ARP transaction, it's completed. So there's nothing else to do here. It's reached its layer 3 destination. There's no layer 4, 5, 6, 7 data. PCB isn't requesting anything to be sent back. So that ARP flow is done. So now PCA can go back to its original message that it wanted to send, and it can complete that layer 2 header based off the information that's in its ARP table now. So PCA looks in its ARP table, and it sees that the IP address of 1.1.1.2 is mapped to MAC address of all B's. It puts all B's as the destination MAC address on the layer 2 header, and it can now send this message out. This message then gets received by PCB. This is the flow now. So we've gotten our message from PCA to PCB. We've had to use the ARP table to construct the layer 2 header, but we didn't have an entry in the ARP table on PCA, so we had to use an ARP request, send that out as a broadcast. The intended layer 3 receiver of that gets that ARP request, sends an ARP reply back, and now PCA was able to complete its ARP table and reconstruct the full layer 2 header. So a couple other things to note here is that the ARP tables are updated based on received packets. So it's on ingress. And for dynamic entries, again, at the beginning we talked about you can have static entries, but most of the time you use dynamic ARP tables. And so it's based off of the traffic that it's seeing in transit there. Dynamic ARP entries, they have a countdown timer. So when traffic is received and when an endpoint receives a packet, if it already has that entry in its ARP table for the combination of the source MAC address and IP address, if it has that entry in there already, then it just resets that timer back to its starting point. When that timer expires, though, that entry is removed from the ARP table. So that's how these tables stay dynamic and not basically buffer overflow and memory leaks because they just grow and grow and grow. So there is a purging of it that happens dynamically. The last thing I wanted to mention about this is that some devices are configured for gratuitous ARP. So since ARP requests are layer 2 broadcasts, it can create a lot of noise on the network as devices are trying to figure out what these MAC address mappings are. So some devices, when they join a network, they will actually send out a gratuitous ARP, which means they're just going to send a broadcast out to everything saying, hey, here I am on the network. This is my IP address. Here's my MAC address. And that destination for it is going to be a layer 2 broadcast address, all Fs. Final thing on this, I want to make sure is very clear, is that the ARP table, it only contains IP to MAC address mappings for its local network. So if a device wants to send a message to an IP address that is not part of its local network, then the message gets sent to the MAC address of the default gateway, and then the default gateway handles getting the message to other networks. This is covered more in the PC communication with a router, but I just want to emphasize that ARP tables are only for IP addresses that are part of the endpoint's local network.